Look up at the night sky on a clear evening, and it's easy to think of space as something tranquil, even timeless. But out there, in the unimaginable depths of the cosmos, titanic events are unfolding on a scale so vast it defies human comprehension. Among the most spectacular of these are galactic collisions, cosmic car crashes involving hundreds of billions of stars, unfolding in breathtakingly slow motion over hundreds of millions of years. And one of the most stunning examples of this violent celestial dance is happening right now in a pair of galaxies known as NGC 4672, more famously called the Mice Galaxies. Located about 300 million light-years from Earth, these two spiral galaxies are caught in a gravitational embrace, pulling and stretching each other into long, luminous tails that stream across the darkness like the tails of two celestial mice, giving the system its unforgettable name. But the beauty of the Mice Galaxies is more than skin-deep. Within those vast, swirling clouds of gas and dust, amid the slow-motion chaos of this collision, something extraordinary is taking shape. Galactic collisions like this one are cosmic crucibles, places where the ordinary rules of physics are bent, twisted, and sometimes completely rewritten. They are factories of the strange and the spectacular, birthing objects and phenomena so bizarre they challenge our very understanding of the universe. From supermassive black holes flung out of their host galaxies to star clusters shining with the light of millions of suns, the Mice Galaxies are home to some of the most mysterious and awe-inspiring structures ever observed. And that's exactly what we're going to explore together today. In this video, we're setting off on a journey deep into the heart of this epic collision to uncover 30 of the strangest objects hidden within the Mice Galaxies. We'll encounter stellar nurseries blazing with newborn stars, dark matter bending the fabric of space-time, and gravitational anomalies that even astronomers are still struggling to explain. This isn't just a tour of pretty pictures, it's an invitation to witness the raw, creative, and often violent forces that shape galaxies, forge worlds, and occasionally rewrite the rules of the cosmos itself. So settle in, open your mind, and let's dive into one of the most fascinating and mysterious corners of our universe. Our journey into the heart of this cosmic collision begins with the most fundamental feature of any galaxy, its core. In most spiral galaxies, you'd expect to find a single, brilliant nucleus, often home to a supermassive black hole. But the Mice Galaxies are not like most galaxies. Within the swirling chaos of their merging forms, astronomers have discovered not one, but two distinct, active nuclei shining brightly at the center of each galaxy. This is our first strange object, the twin nuclei. Identifying these cores was a monumental task. To the naked eye, or even through an optical telescope, the central regions of the mice appear as a confused, brilliant knot of light, a tangled web of gas, dust, and stars. It took the penetrating gaze of infrared and radio telescopes to cut through that cosmic fog. Infrared light, which is less easily scattered by dust, allowed us to peer directly into the galactic hearts, while radio observations mapped the intense energy pouring out from them. What these observations revealed was astonishing. Both original galaxies have managed to hold onto their supermassive black holes, and both are still actively feeding on the surrounding material, blazing as powerful engines known as active galactic nuclei. This discovery is absolutely crucial to our understanding of how galaxy mergers unfold. It tells us that even in the midst of this incredible gravitational upheaval, the very hearts of these galaxies have remained largely intact. They are like two dancers spinning and pulling at each other's arms, yet their cores remain stable, anchored by the immense gravitational pull of their central black holes. The fact that both are still active indicates that the merger is actually funneling vast quantities of gas and dust toward these central engines, stoking their fires and making them shine even brighter than they might in isolation. This violent, chaotic process isn't just destroying a galaxy. It's feeding the monsters at its center, giving us a front-row seat to the complex and fiery relationship between galactic collisions and the awakening of supermassive black holes. But it's impossible to talk about the hearts of these galaxies without immediately being drawn to the most spectacular feature they've created, a structure so immense it defies belief. As the two galaxies first swung past each other, their mutual gravitational pull didn't just warp their shapes, it reached in and literally pulled them apart. The result is our second strange object, an absolutely colossal tidal tail, an arc of stellar debris stretching an incredible 100,000 light-years out into the intergalactic void. To fully grasp that scale, consider that our entire Milky Way galaxy is roughly 100,000 light-years across. This single structure, ripped from the larger galaxy known as NGC 4676a, is as long as our home galaxy is wide. This isn't a simple stream of light, it's a river of creation and destruction made tangible. The tail is composed of everything that was once part of the galaxy's outer disk, billions of stars, along with enormous clouds of gas and dust, all torn from their gravitational moorings and flung into the darkness. The process that creates this is both elegant and violent. As the two galaxies passed by one another, the force of gravity from the smaller galaxy tugged more strongly on the near side of the larger one than on its far side. This difference in pull, a tidal force much like the moon's effect on Earth's oceans but on an unimaginable scale, stretched the galaxy out, spinning this long material out behind it like celestial taffy. What's truly fascinating is what's happening inside this river of stars. Within those vast clouds of gas and dust, now compressed and agitated by the gravitational turmoil, the conditions for star birth have become perfect. The tail is absolutely brimming with stellar nurseries, regions glowing with the fierce blue light of massive, young stars that simply would not exist had this galactic encounter never occurred. This immense structure is therefore a paradox. It is both a scar from a violent event and a brilliant beacon of new life, a testament to the cosmos's ability to create even as it destroys. It serves as a permanent record of the collision, a fossilized snapshot of the exact moment these two galaxies interacted, whose light has been traveling for 300 million years just to reach our eyes and tell its story. Now, if we follow that river of stars in the tidal tail, our attention is inevitably drawn to a single, brilliant point of light, shining with an intensity that rivals the core of a small galaxy. This is no ordinary star cluster. This is our third strange object, a super-star cluster known to astronomers as NGC 4676 SC1. Hubble Space Telescope observations revealed this object to be an absolutely staggering concentration of stellar firepower. We're looking at a region where millions of stars have been born together, packed into a dizzyingly small volume of space. To understand just how dense this is, consider that the distance from our Sun to its nearest stellar neighbor, Proxima Centauri, is about 4 light-years. Inside a superstar cluster like this, that same amount of space could contain not one, but thousands of stars. The night sky for any hypothetical planet inside this cluster would be a perpetual, dazzling daylight, with stars spaced so closely they would appear as a continuous, glowing fabric. The formation of such an extraordinarily dense and bright object is a direct and violent consequence of the galactic collision. As the two galaxies intermingled, their immense clouds of gas and dust didn't just gently mix, they were slammed together under enormous pressure. Think of it like two weather fronts colliding and creating a supercell thunderstorm, but on a cosmic scale. This sudden, extreme compression triggers a ferocious burst of star formation, what astronomers call a starburst. In these regions, gas clouds collapse not into individual stars, but into entire families of stars all at once. The result is a superstar cluster, a gravitationally bound city of stars, all born from the same turbulent event. What makes NGC 4676 SC1 so fascinating to scientists is that it offers a glimpse into the possible past of our own galaxy. Many astronomers believe that the ancient, dense globular clusters that orbit the Milky Way, like the famous Omega Centauri, may have begun their lives in a very similar way as superstar clusters born in violent galactic encounters during the universe's more chaotic early epochs. Studying this brilliant beacon in the Mice Galaxies allows us to watch this process unfold in real time, providing a crucial key to understanding how some of the oldest structures in our own cosmic neighborhood came to be. It is a direct and luminous link between the colossal drama of a modern collision and the deep, ancient history of galaxy formation itself. But as spectacular as the visible light from these star-forming regions is, it only tells part of the story. To uncover the full, frenetic scale of the creation happening here, we need to look at the Mice Galaxies through a different set of eyes that can see the heat. When astronomers pointed infrared telescopes like the Spitzer Space Telescope toward the smaller of the two mice, known as NGC 4676b, they discovered our fourth strange object, an infrared luminous core shining with a ferocious, hidden intensity. While the galaxy's visible light appears somewhat subdued, its heart is absolutely blazing in the infrared spectrum, glowing with the warmth of a truly immense number of newborn stars. This incredible infrared output is a classic signature of a phenomenon known as a dust-enshrouded starburst. Here's what that means. The violent collision of the two galaxies has funneled a tremendous amount of gas and dust directly into the core of NGC 4676b. This material is the raw fuel for star formation, and it's igniting a firestorm of stellar birth. Thousands, perhaps even millions of massive, hot, young stars are being forged in this cramped, chaotic region. But these brilliant new stars are immediately blanketed by the very same thick clouds of gas and dust that created them. This cosmic cocoon absorbs their intense visible and ultraviolet light, heating up until it glows brilliantly itself, re-radiating all that captured energy outward as infrared light. This process reveals a fundamental truth about galactic mergers. The most intense action is often hidden from plain view. The visible light shows us the graceful tidal tails, but the infrared light exposes the true engine room of the collision. The amount of energy pouring out of this core tells us that the star formation rate here is staggering, orders of magnitude higher than what we see in a quiet galaxy like our own Milky Way. This isn't just a few new stars, this is a wholesale, runaway production of stellar bodies, a veritable factory operating at maximum capacity, hidden behind a veil of its own making. It's a dramatic example of how these cosmic encounters don't just rearrange stars, they fundamentally reignite a galaxy's heart, turning it into a powerhouse of creation that can outshine everything else around it, even if we need special tools to see its true glory. While the infrared view reveals hidden stellar nurseries, another part of the electromagnetic spectrum exposes an even more violent and extreme side of this galactic collision. To see it, we had to turn to the Chandra X-ray Observatory, a telescope designed to see the universe in the high-energy light of X-rays. Its gaze into the heart of the mice revealed our fifth strange object, an incredibly bright, point-like source of X-rays, catalogued as one of the most luminous of its kind ever observed. This isn't a cloud of hot gas or a diffuse glow. It's a precise, brilliant beacon signaling a catastrophic event on a stellar scale. Astronomers identified this object as what's known as an ultraluminous X-ray source, or ULX for short, and the prevailing theory is that we are looking at an X-ray binary system operating at the absolute extreme edge of physics. So, what exactly is happening here? This intense X-ray light is believed to be the final scream of matter being devoured. The system likely consists of two objects, a normal star similar to our Sun, and an incredibly dense stellar remnant, either a neutron star or a stellar mass black hole. These two objects are locked in a tight, deadly orbit. the immense gravitational pull of the dense remnant is actively stripping material away from its companion star. This stolen gas doesn't fall directly in. Instead, it forms a swirling, superheated disk around the predator object, known as an accretion disk. As the gas spirals inward at nearly the speed of light, it is compressed and heated to temperatures of millions of degrees, causing it to glow with an intense fury that we detect as X-rays. The sheer brightness of this source suggests an almost unimaginable feeding rate, a cosmic feast of stellar material. The reason this object is so important, and why it's classified as a strange object within the mice, is its direct link to the galactic merger itself. While X-ray binaries can exist in isolated galaxies, they are relatively rare. Galactic collisions like this one act as a trigger mechanism, dramatically increasing their numbers. The gravitational turmoil of the merger does two things. First, it stirs up the interstellar medium, funneling vast amounts of gas into galactic centers and providing the raw fuel for such systems to form. Second, and perhaps more importantly, the close encounters between stars can create the perfect conditions for these deadly partnerships. A neutron star or black hole, which might have been drifting alone through its galaxy, can have its orbit altered by a passing star, throwing it into a path that eventually captures a stellar companion. The collision, in essence, is setting the table for these cosmic predators, making them far more common than they would be in a quiet, undisturbed galaxy. Studying this brilliant X-ray source gives us a unique laboratory to understand some of the most extreme physical processes in the universe. The temperatures, densities, and gravitational forces at work here are so intense that they push the limits of our models for how matter and energy behave. By analyzing its light, we can probe questions about the nature of the accreting object itself. Is it a black hole? And if so, how fast is it spinning? Is it a neutron star with a magnetic field trillions of times stronger than Earth's? Each flicker and flare in its X-ray output tells a story of physics under conditions we could never hope to recreate on Earth, offering a front-row seat to the most violent and energetic relationships in the cosmos. Now, as we follow that immense river of stars, the 100,000 light-year-long tidal tail, we arrive at perhaps one of the most profound and puzzling structures within this entire collision. Near the very tip of that sprawling arc of debris, astronomers have pinpointed a massive, condensed knot of gas and stars that shines with a surprising degree of independence. This isn't just another clump of material. The evidence strongly suggests we are looking at a celestial object in the act of being born. This is our sixth strange object, a tidal dwarf galaxy candidate, a potential new galaxy forging its own identity from the wreckage of a cosmic catastrophe. The concept itself is almost poetic. Here we have two large, mature galaxies tearing each other apart through their immense gravitational pull. And yet, from that very act of destruction, the raw materials are being gathered to potentially build something entirely new. The material in this knot wasn't born there. It was ripped from the outer disks of the parent galaxies during their first close pass. This ejected gas and dust, now free from the stronger gravitational pull of the original galactic cores, has begun to collapse under its own gravity. Within this condensation, the telltale signs of a galaxy in its infancy are beginning to show. Observations reveal it is not just a passive collection of stars, it is a dynamic region, rich with the cold, dense molecular gas that is the essential fuel for ongoing star formation. New stars are being born here from the ashes of the old, giving this object its own source of light and energy. What truly sets this candidate apart and makes the case for its potential independence is its composition. Unlike its parent galaxies, which are believed to be shrouded in massive halos of invisible dark matter, this budding galaxy appears to be made almost exclusively of baryonic matter, the ordinary atoms that make up stars, planets, and us. This is a critical piece of evidence because it formed from material stripped from the galactic disks, where dark matter has less influence. The candidate likely contains very little of this mysterious substance. If it can achieve a stable, gravitationally bound structure without a dominant dark matter halo, it would challenge some of our fundamental assumptions about what is absolutely necessary for a galaxy to form and endure. It becomes a pure laboratory of visible matter, showing us how stars and gas can coalesce on their own terms. The future of this object is a fascinating open question. Over the next several billion years, one of several paths awaits it. It might successfully condense further, its own gravity triumphing to form a stable, if small, independent dwarf galaxy that will orbit the merged remains of the Mice system as a permanent satellite, a living fossil of the collision. Alternatively, as the two main galaxies complete their merger and settle into a new, larger elliptical galaxy, their renewed gravitational pull could reach out and recapture this wayward child, pulling the tidal dwarf back in and re-assimilating its stars. Or if it doesn't have quite enough mass to hold itself together, it could simply slowly dissipate, its stars scattering into the lonely intergalactic void. By studying this candidate, we are getting a rare glimpse into the life cycle of galaxies themselves, witnessing not just their death, but also the potential for their rebirth, all within the same breathtaking cosmic event. But the story of these two brilliant hearts doesn't end with their mere existence. The truly captivating idea, and our seventh strange object, is the possibility that we are not just looking at two supermassive black holes, but a double-active galactic nucleus. This means both central black holes are not just present, they are actively feeding, accreting vast amounts of matter and releasing unimaginable amounts of energy as they do so. For astronomers, confirming this is like finding two volcanoes erupting simultaneously on two different continents. It speaks to a global, interconnected process of immense power. The observational evidence for this double activity is a masterclass in cosmic detective work. Peering into the bright, dusty core of a single galaxy is difficult enough. Disentangling the light from two separate, yet incredibly close, energetic cores is a monumental challenge. It requires moving beyond the capabilities of optical telescopes. The key proof comes from combining observations across the electromagnetic spectrum. Radio telescopes, like the Very Large Array, have been crucial, mapping the precise locations of incredibly bright, compact sources of radio waves, a classic signature of the powerful jets often launched by actively feeding supermassive black holes. Meanwhile, the Chandra X-ray Observatory has pinpointed intense, point-like sources of high-energy X-rays emanating from these same locations, radiation that is produced in the searingly hot accretion disks just outside the black hole's event horizons. When these precise locations from different wavelengths align, it builds a compelling case that we are indeed witnessing two separate engines roaring to life at once. This leads to the fundamental question: why would a galaxy merger trigger such phenomenal activity in these otherwise dormant giants? The answer lies in the chaos of the collision itself. In an isolated, tranquil spiral galaxy like our Milky Way, the central supermassive black hole is often starved of fuel. Gas and dust orbit in stable, serene patterns, largely avoiding the plunge into the central gravitational well. A galactic merger acts as the ultimate disruptor. It is a cosmic blender that violently churns the contents of both galaxies, throwing orderly orbits into disarray. Vast rivers of interstellar gas, which might have peacefully drifted for billions of years, are suddenly funneled directly toward the two cores. This provides an enormous and sudden feast for the black holes, causing them to awaken from their slumber and begin accreting material at a ferocious rate. As this matter spirals inward at near light speed, it forms an accretion disk that is heated to temperatures of millions of degrees, causing it to glow across the entire spectrum from ultraviolet to X-rays. This is the active galactic nucleus we observe. The fact that both black holes are active simultaneously tells us that the merger is efficient at delivering fuel to both cores at the same time, a testament to the sheer scale of the gravitational upheaval. We are essentially watching the triggering mechanism for some of the most powerful engines in the universe, a process that shapes not only the galaxies involved but also their future. The energy released by these active nuclei can drive powerful winds that blow away remaining gas, effectively shutting down future star formation and ultimately determining the final form of the merged galaxy. The double-active nucleus is therefore more than just a pair of lights. It is the fiery crucible where the fate of an entire galactic system is being decided. While the X-ray and infrared data reveal the intense feeding frenzy at the galaxy's cores, another form of observation unveils an even more dramatic and far-reaching effect of this activity. When astronomers turned powerful radio telescopes toward the mice, they detected something astonishing: vast, structured lobes of emission billowing out from the system. This is our eighth strange object, mysterious and powerful radio jets. These are not simple waves of energy. They are focused beams or jets of superheated plasma being launched at nearly the speed of light from the very vicinity of the supermassive black holes, and their effect on the surrounding environment is nothing short of transformative. To understand what creates these colossal jets, we need to picture the extreme physics happening just outside the black hole's event horizon. Not all the material spiraling inward in the accretion disk is doomed to fall in. Through processes involving immense magnetic fields and the incredible rotational energy of the black hole itself, a fraction of this superheated gas is channeled away from the poles and accelerated outward into two oppositely directed, incredibly narrow beams. This is akin to placing your thumb over the end of a garden hose to create a powerful, focused stream, but on a scale where the hose is light years across and the water is a plasma hotter than the core of a star. The particles within these jets, primarily electrons, travel along magnetic field lines and emit synchrotron radiation across the radio spectrum as they do, which is how our telescopes can trace their incredible journey. The true impact of these jets is seen in what happens when they slam into the intergalactic medium, the thin soup of gas and dust that exists in the vast spaces between galaxies. The jets act as cosmic blowtorches, plowing into this material and pushing it aside, creating enormous cavities and shock waves that ripple outward for thousands of light years. These radio lobes are the evidence of that interaction. They are the hotspots where the jets terminate and dissipate their enormous energy, lighting up like celestial road marks. This process injects a tremendous amount of energy and heat into the surrounding void, effectively sculpting the environment on a galactic scale. It can prevent the nearby gas from cooling and collapsing to form new stars in satellite galaxies, and it can even regulate the flow of material back onto the merging galaxies themselves. In this way, the jets are a powerful feedback mechanism. The energy released by the black hole's feast directly influences the future supply of their own food, a breathtaking example of the universe's self-regulating nature. Scattered across the turbulent bodies of the Mice Galaxies, like brilliant sapphires strewn on velvet, are countless intensely blue knots that dominate any Hubble Space Telescope image. These are not single stars, but our ninth strange object, massive star-forming regions, colossal stellar nurseries where the collision has ignited a firestorm of creation. Their striking blue color is the first clue to their nature, a direct result of the incredible heat and mass of the stars being born within them. The most massive stars burn extremely hot, and hot stars emit the majority of their light in the blue and ultraviolet part of the spectrum. Because these regions are producing a phenomenal number of these massive, short-lived, brilliant stars all at once, their collective light overwhelms everything else, painting these knots in the most vivid cosmic blue. The reason these regions exist in such abundance is a direct and violent consequence of the galactic merger. In a quiet, undisturbed spiral galaxy, star formation is a relatively orderly, slow process. Giant molecular clouds may eventually collapse under their own gravity, but it can take millions of years. Here, the collision has acted like a cosmic blender on an unimaginable scale. The gravitational forces at work during the close pass of the two galaxies sent powerful shockwaves racing through their interstellar mediums. These shockwaves did not gently nudge the clouds of gas and dust. They slammed into them with immense pressure, compressing them to densities far beyond what would ever occur naturally. It's the difference between gently squeezing a fistful of snow and packing it into a tight, hard snowball and hurling that snowball into a wall. The sudden, extreme compression triggers a chain reaction of collapse, igniting not just one star at a time, but entire clusters of stars simultaneously in a ferocious burst of activity astronomers call a starburst. A Hubble image of the mice is therefore not just a pretty picture, it's a detailed map of this ongoing celestial violence. Each brilliant blue knot is an epicenter of this starburst activity. The telescope's exquisite resolution allows us to peer into some of these regions and resolve them, not as a single blur of light, but into the individual, searingly hot stars that power them. We can see the intricate structures within the nebulae, the dark, twisting lanes of dust that are the raw material for future stars, and the fierce stellar winds from the newborn stars already beginning to blow cavities in the very gas that created them, sculpting the nebula and eventually shutting off the star formation process. This creates a fascinating life cycle visible in a single frame. Some knots are still deeply enshrouded in their birth cocoons, while others have already cleared their surroundings, their brilliant blue stars now exposed and blazing across the darkness. The sheer intensity of these regions has profound implications for the future of the Mice Galaxies. This rampant star formation is effectively a blaze of glory that consumes a galaxy's most precious resource, its cold gas. The massive stars born in these blue knots live fast and die young, ending their short lives in spectacular supernova explosions within just a few tens of millions of years. These explosions will scatter heavy elements forged in their cores throughout the galaxies, enriching the interstellar medium with the building blocks for planets and future life. But they will also blow away any remaining gas with tremendous force, and the intense radiation from the living stars is already doing this, heating and dispersing the gas reservoirs. This means that after this starburst phase concludes, the merged galaxy will have largely exhausted its fuel for making new stars. The brilliant blue knots are both the spectacular highlight and the beginning of the end for star formation in this system, a breathtaking but finite burst of creativity that will ultimately leave behind a quieter, older galaxy. Yet for all the violence and brilliance we can see, from the blazing star clusters to the roaring black holes, they account for only a tiny fraction of the true mass of the Mice Galaxies. The overwhelming bulk of the material in this system is completely invisible, detectable only by its ghostly gravitational pull. This, of course, is dark matter, the mysterious substance that makes up about 85% of the matter in the universe. And in a galactic collision, this unseen component behaves in a way that is utterly counterintuitive, creating our 10th strange object, a profoundly unusual and revealing dark matter distribution. To map something that emits no light whatsoever, astronomers rely on a phenomenon known as gravitational lensing. The theory, stemming from Einstein's general relativity, states that a massive object will warp the very fabric of spacetime around it. This warping acts like a lens, bending and distorting the light from more distant galaxies that happen to lie directly behind it from our point of view. By carefully studying the specific patterns of this distortion, how those background galaxies are stretched into faint arcs and smears, scientists can create a detailed mass map of the foreground object. It's a way of weighing a galaxy and pinpointing where its mass is concentrated, all without seeing the mass itself. When this powerful technique was applied to the Mice Galaxies, the results were startling. In a simple, isolated spiral galaxy, we expect to find a massive, roughly spherical halo of dark matter that extends far beyond the visible edge of the stars and gas. The visible galaxy is just the bright, dense core embedded within this much larger, invisible sphere of mass. the collision in the Mice has completely scrambled this expected arrangement. The dark matter halos of the two galaxies appear to have passed right through one another during their initial encounter. Unlike the stars and gas, which interact spectacularly, slamming together to trigger star formation and being pulled out into long tidal tails, the dark matter particles theoretically only interact with each other and with normal matter through gravity. With no other forces like electromagnetism to cause friction or collisions, the two dark matter halos simply slipped through each other like two ghosts passing in the night. This leads to the bizarre and profound revelation from the lensing maps. The largest concentrations of total mass, and therefore the peak of the dark matter distribution, are no longer perfectly aligned with the brightest clumps of stars or the active galactic nuclei. There's a detectable offset, a slight but significant separation between where most of the visible matter has ended up and where the gravitational lensing tells us the bulk of the mass actually resides. This is a direct observational signature of dark matter's elusive nature. It proves that this mysterious substance truly is something other than ordinary atoms. It behaves differently under extreme conditions, and a galactic collision is the ultimate laboratory for testing this behavior. The implications of this odd distribution reach far beyond this single pair of galaxies. It provides some of the strongest indirect evidence for the existence of dark matter as a distinct physical entity. Alternative theories of gravity that try to explain away the need for dark matter by modifying Einstein's equations struggle to account for this observed separation between the visible mass and the gravitational mass in colliding systems like the Mice. Furthermore, studying how these dark matter halos are behaving, how they are sloshing, merging, and eventually settling gives us crucial clues about the properties of the dark matter particles themselves. The fact that the halos pass through each other so freely suggests that dark matter particles are likely cold, meaning they move relatively slowly, and they have a very low cross-section, meaning they rarely, if ever, collide with each other. This cosmic collision has, in effect, allowed us to weigh and probe the nature of the universe's most dominant yet most mysterious component, using gravity itself as our guide. While the optical image shows two distinct galaxies connected by a magnificent tail of stars, this visible light is only part of the story. To see the full, breathtaking scope of this cosmic connection, we needed to look with different eyes that can see the cold, dark gas that is the true lifeblood of a galaxy. When astronomers pointed the immense radio telescopes of the Very Large Array toward the Mice, they revealed our 11th strange object, a colossal and diffuse intergalactic hydrogen bridge, a vast river of primordial gas flowing between the two galaxies that is completely invisible to optical telescopes. This isn't a structure made of stars, it's a reservoir of raw potential. The bridge is composed of neutral hydrogen, the most basic and abundant element in the universe, the fundamental building block from which everything else, stars, planets, and life itself, is forged. Detecting this faint signal was a technical marvel. Hydrogen atoms in space naturally emit a faint radio wave at a very specific frequency, 21 centimeters. By tuning their massive radio dishes to listen for this specific cosmic whisper, astronomers were able to map the distribution of this gas in stunning detail. What they found was a continuous, tenuous stream linking the bodies of the two mice, a testament to the gravitational forces that pulled it out into intergalactic space during the galaxy's first close encounter. The existence and behavior of this hydrogen bridge reveal profound truths about the mechanics of galactic mergers. Unlike stars, which are like individual specks of sand that mostly pass by each other without colliding in the vastness of space, the gaseous components of galaxies behave more like a fluid. When the two galaxies interacted, their mutual gravity pulled not only on the stars but also on these enormous clouds of hydrogen. The gas, being more susceptible to tidal forces, was stretched out between them, forming this immense arching bridge. It acts as a direct pipeline, channeling material from one galaxy to the other and into the surrounding environment. This transfer of gas is a critical process, as it can starve one galaxy of the fuel needed for future star formation while simultaneously feeding a starburst in the other. What's truly fascinating about this structure is its future. This river of cold hydrogen hanging in the void is not permanent. It is the site of a quiet but relentless transformation. Within this bridge, pockets of gas are slowly collapsing under their own gravity, without the fierce radiation from existing stars to heat it up and prevent collapse, a common issue within crowded galaxies. This isolated gas can cool and condense more efficiently. This makes the intergalactic bridge a potential breeding ground for a unique and exotic population of stars. We could be witnessing the very early, quiet beginnings of star formation occurring in profound isolation, far from the bright lights of the galactic disks, giving birth to stars that will live and die in the darkness between galaxies. This vast, invisible structure is therefore much more than a relic of a past gravitational pull. It is a dynamic and evolving feature, a cosmic umbilical cord that is still shaping the fate of the entire system. Amidst all these colossal, slow-moving structures, the tidal tails, the dark matter halos, the star-forming regions, the universe sometimes reminds us that it can also produce events that are spectacularly fleeting. In 2018, a team of astronomers poring over data from a monitoring campaign of the Mice Galaxies spotted something that wasn't there before, a single, brilliant point of light that had suddenly flared into existence. This is our 12th strange object, an unidentified transient, an astronomical event that blazed with incredible intensity and then, just as suddenly, faded back into obscurity, leaving behind a compelling mystery. The immediate task for scientists was to classify this flash. In the chaotic environment of a galactic merger, several cosmic catastrophes could fit the bill. The most common culprit for such a sudden appearance is a supernova, the explosive death of a massive star. In a starburst region like the Mice, which is producing so many massive, short-lived stars, the rate of supernova should be significantly higher than in a normal galaxy. However, the observed light curve, the specific way the object's brightness changed over time, didn't perfectly match the known patterns of common supernova types. It was either a very unusual supernova or it was something else entirely. This led researchers to consider a more exotic and violent possibility, a tidal disruption event or TDE. This occurs when a star wanders too close to a supermassive black hole. The black hole's immense tidal forces, the same kind that created the galaxy's vast tails but on a much smaller and more violent scale, will stretch and compress the star, literally pulling it apart into a stream of gas. This material then rains down onto the black hole's accretion disk, causing a temporary but brilliant flare of radiation as it is consumed. The merger environment of the Mice, with its stirred-up stellar orbits and active nuclei, is a perfect hunting ground for such rare events, as stars can be easily thrown onto perilous paths near the central black holes. Yet, the evidence remained inconclusive. The transient's behavior had peculiarities that didn't cleanly align with a standard tidal disruption event model either. This opened the door to a far more exciting, though frustrating, possibility that this flare represented a completely unknown type of astrophysical event. Perhaps it was a star being torn apart by an intermediate mass black hole, a class of object that is notoriously difficult to find. Or maybe it was something even more exotic, related to the extreme physics of the ongoing merger itself that we don't yet fully understand. The ultimate fate of this object is what makes it so fascinating and emblematic of modern astronomy. Before its nature could be definitively determined, it faded from view. Without a continuous, long-term monitoring campaign specifically watching that exact spot, the crucial data needed to solve the mystery was lost. This transient object is a perfect example of a growing class of phenomena discovered in the era of automated all-sky surveys events that are here one moment and gone the next, leaving behind a single data point that challenges our existing catalogues of cosmic violence. It underscores a fundamental truth about the universe. For all our powerful telescopes and advanced theories, we are still only glimpsing a fraction of the dynamic and explosive events unfolding in the darkness. As we continue to map the intricate structure of this cosmic wreck, a particularly curious feature emerges around the smaller of the two galaxies, NGC 4676b. Detailed observations suggest that this galaxy might be in the process of forming an exceptionally rare and spectacular configuration, a polar ring. This is our 13th strange object, a structure that, if confirmed, would see a grand luminous ring of stars, gas, and dust orbiting the galaxy over its poles, perpendicular to its main disk, like a celestial hula hoop spinning around a central egg. To understand just how unusual this is, you must first picture a typical spiral galaxy. It's a relatively flat disk, like a fried egg, with everything stars, gas, planets orbiting in a more or less orderly fashion around a central bulge, all within the same general plane. A polar ring galaxy shatters that two-dimensional simplicity. It's a three-dimensional cosmic hybrid, where a central lenticular or elliptical galaxy is encircled by an outer ring of material that orbits at a nearly 90-degree angle to the central galaxy's plane. This ring isn't just a wispy illusion. It can contain as much mass and as many stars as the central galaxy itself, making it a fundamental and dominant component of the entire system. These structures are incredibly rare in the universe, making any potential candidate a subject of intense scientific fascination. The prevailing theory for how such a bizarre configuration forms almost always involves a galactic merger or a very close encounter. It's a scenario of cosmic theft and gravitational manipulation. The idea is that a smaller, gas-rich dwarf galaxy ventures too close to a larger galaxy on a specific perpendicular orbit. The larger galaxy's gravity violently strips the dwarf of its stars and gas, but instead of this material simply falling in or being scattered, the unique orbital dynamics come into play. The captured material doesn't settle into the existing disk. Instead, it begins to orbit around the galaxy's poles, gradually settling into a stable, rotating ring over hundreds of millions of years. It's a delicate balancing act. The gravitational forces have to be just right for the ring to form and persist, rather than the material simply being absorbed or flung away entirely. In the case of the mice, the suspected polar ring is forming from the ultimate source, its merging partner. The colossal gravitational forces at play during the collision are pulling vast streams of material from the larger galaxy and flinging it in all directions. Some of this material, according to kinematic models and observations of its motion, appears to be settling into a stable orbit that is drastically tilted relative to the smaller galaxy's original disk. This isn't a clean, pre-existing dwarf galaxy being consumed. It's a ring being forged in the chaos of the merger itself, built from the very debris of its partner. This makes the potential polar ring in the mice a unique and dynamic object, one we are catching in the very act of its formation, providing an unprecedented opportunity to study the physics behind the creation of these rare galactic hybrids. Studying this candidate structure offers far more than just the confirmation of a cosmic oddity. A stable polar ring acts as a natural laboratory for probing the invisible architecture of a galaxy, its dark matter halo. Because the ring orbits at a different angle than the main disk, it essentially traces the gravitational field of the galaxy in 3 dimensions. By meticulously mapping the rotation and velocity of the gas and stars within the ring, astronomers can construct a detailed 3-dimensional model of the galaxy's gravitational potential. Since gravity is a direct proxy for mass, this allows scientists to precisely weigh the galaxy and, crucially, map the shape of its invisible dark matter halo. The results from other polar ring galaxies suggest these halos are not perfect spheres, but are instead flattened, almost like a squashed beach ball. Any data from the Mice system would provide a crucial new data point in our understanding of how dark matter behaves and distributes itself during the extreme event of a merger. The future of this nascent ring is still uncertain. It may stabilize into a permanent, defining feature of the post-merger galaxy, a breathtaking ringed monument to the violence of its creation that will persist for billions of years. Alternatively, the ongoing merger dynamics could prove too disruptive, preventing the ring from achieving a stable configuration and causing it to eventually dissipate or be absorbed. By monitoring this object, we are essentially watching a real-time test of gravitational theory and galactic evolution, a chance to witness the birth of one of the universe's most majestic and enigmatic structures. While the brilliant light shows from active nuclei and starbursts are spectacular, the ultimate fate of the Mice Galaxies' twin hearts involves a phenomenon that emits no light at all, yet will ripple the very fabric of the universe. Locked in their slow gravitational dance, the two supermassive black holes are destined to spiral ever closer, and their final merger will be one of the most violent events conceivable, generating powerful ripples in space-time known as gravitational waves. This prospect offers a glimpse into a future billions of years from now and stands as one of the most exciting possibilities for the future of astronomy. The journey to this cosmic collision is an achingly slow process governed by physics. Currently, the two black holes are likely separated by thousands of light years, embedded in the dense cores of their respective galaxies. Their initial inward spiral is driven by a mechanism known as dynamical friction. As they move through the crowded stellar environment of the merging galactic core, their immense gravity pulls on the surrounding stars, effectively creating a gravitational wake that drags behind them. This wake acts like a cosmic brake, sapping the black hole's orbital energy and causing them to gradually sink toward the common center of mass of the new merged galaxy. This process alone could take 100 million years or more. Once they draw close enough that their mutual gravitational pull becomes the dominant force, perhaps within a few light years of each other, a new and even more precise phase begins: stellar scattering. At this range, the black holes can be thought of as a binary system, and their gravity will fling away any star that ventures too close. By ejecting these stars from the galaxy's core, the binary black holes further lose orbital energy, tightening their dance. The final stage of this incredible process is reached when they are just a few hundredths of a light year apart. Here, the only efficient way to shed their remaining enormous orbital energy is through the emission of gravitational waves, as predicted by Einstein's theory of general relativity. This is where the event transitions from a slow cosmic drift to a catastrophic finale. As the black holes whip around each other at a significant fraction of the speed of light, they distort spacetime itself, sending out these waves like ripples from a stone thrown into a pond. The waves carry away energy, causing the orbits to decay further and further until the two colossal objects finally plunge together and merge into a single, more massive black hole. The resulting collision would release more energy in a fraction of a second than all the stars in the observable universe combined, almost all of it in the form of gravitational waves. For astronomers, detecting the gravitational waves from such a merger would be the ultimate prize. The Laser Interferometer Space Antenna, or LISA, a planned European Space Agency mission, is specifically designed to hunt for these low-frequency ripples from supermassive black hole mergers. The signal from an event like the eventual merger in the Mice would be a prime target. It would provide unparalleled data to test the limits of general relativity under the most extreme conditions imaginable and offer a direct window into the properties of the black holes themselves, their masses, their spins, and their orientations. By studying the waveform, the specific pattern of the ripples, scientists could essentially hear the story of the merger, learning details about the encounter that light alone could never reveal. The timeline for this event, however, stretches the definition of future. The complete merger of these two supermassive black holes is likely billions of years away, far longer than the current age of the entire collision we are witnessing now. We are seeing the system as it was 300 million years ago. By the time their final spiral concludes, our own sun may have long since died. Yet, by studying systems like the mice now, we are building the predictive models that will allow future astronomers, or perhaps their advanced AI counterparts, to know exactly where and when to point their instruments, listening for the faint echo of a collision we predicted eons ago. Now, if we shift our perspective from these grand structures and violent events to the very chemical makeup of the stars themselves, we uncover a more subtle but equally profound mystery within the Mice Galaxies. This brings us to our 15th strange object, a peculiar and telling metallicity gradient. In astronomy, metallicity is a term that might sound a bit misleading. It doesn't refer to chunks of iron or aluminum, but rather to the abundance of any element heavier than hydrogen and helium. These heavier elements, which astronomers collectively call metals, are forged in the nuclear furnaces of stars and are then scattered into space when those stars die in supernova explosions. They are the building blocks for rocky planets and ultimately for life itself. Normally, in an isolated spiral galaxy, you would expect to find a smooth and predictable gradient in metallicity. The central regions, which have undergone more generations of star formation and death, are typically metal-rich, while the outer edges, where star formation has been slower and less prolific, remain more pristine and metal-poor. The Mice Galaxies completely upend this expectation. The colossal collision has acted like a cosmic chef, violently stirring the galactic pot and creating a chaotic and uneven distribution of these heavy elements. The intense, compressed starbursts we see in those brilliant blue knots are working at a breakneck pace, consuming vast amounts of primordial hydrogen and helium to produce massive stars. These stars live fast, die young, and explode, seeding their immediate surroundings with a sudden, enormous injection of newly forged metals elements like oxygen, carbon, and iron. This creates localized pockets or bubbles of incredibly enriched material. Meanwhile, the tidal forces have pulled out streams of gas and stars from the inner and outer parts of the original galaxies and flung them far into the tails and the intergalactic bridge. This process has mixed these different populations in a way that would never happen in a calm galaxy. You can now find pockets of old, metal-poor stars from the galactic outskirts existing right next to clouds of gas that are super-enriched with the products of the recent starburst. This strange metallicity pattern is more than just a chemical curiosity. It's a powerful diagnostic tool, a cosmic fingerprint that allows astronomers to reconstruct the history of the collision itself. By meticulously mapping the abundance of these heavy elements across different regions, comparing the tidal tails to the galactic cores, and the star-forming knots to the quiescent regions, scientists can trace the flow of material. They can identify which structures were formed from gas stripped from the inner disks, already somewhat metal-rich, and which came from the more pristine outer halos. It reveals the efficiency of the mixing process and tells us how effectively a galactic collision can redistribute the ingredients for planet formation throughout a system and even into intergalactic space. The unusual gradient is a direct chemical record of the violence, a snapshot of the chaos that simultaneously creates new metals in furious bursts and then flings them across hundreds of thousands of light years, forever altering the chemical future of everything that forms thereafter. These immense shock fronts are essentially cosmic sonic booms, moving through the interstellar medium at incredible speeds and sculpting the gas and dust in their path. To understand their origin, picture the galactic collision not as a simple merging of two soft clouds, but as the high-speed interaction of two complex systems, each with its own velocity, density, and pressure. As the galaxies first swung past each other, their disks filled with gas did not pass through one another smoothly. Instead, the gas clouds from each galaxy slammed into each other head-on. This sudden, violent compression created powerful pressure waves that radiated outward from the point of impact, much like the bow wave that forms at the front of a ship plowing through the ocean. These are the tidal shock fronts, and their visibility is a direct testament to the sheer force of the interaction. What makes these structures so revealing is that they act as a natural laboratory for studying fluid dynamics on a galactic scale. The interstellar medium, for all its vastness, behaves in many ways like a fluid, and these shock waves moving through it obey the same fundamental laws of physics that govern air rushing over an airplane wing or water flowing around a rock. The key difference is one of almost unimaginable scale. By studying the shape, density, and velocity of these visible fronts, astronomers can literally measure the speed and direction of the collision. The compressed gas within the shock wave glows brightly, often in specific wavelengths of light that denote its composition and temperature, allowing scientists to calculate the immense pressures and energies involved. These are not static sculptures, they are dynamic, evolving features that chart the transfer of energy from the orbital motion of the galaxies into the turbulent motion of their internal gases. Perhaps the most crucial role these shock fronts play is in triggering the very star formation we see lighting up the galaxies. The passage of a shock wave does not simply push gas aside, it violently compresses it. Imagine a vast, placid cloud of hydrogen gas drifting slowly through its galaxy. Suddenly, a wall of pressurized gas, driven by the gravitational energy of the collision, slams into it. The cloud is forced to collapse rapidly under the immense external pressure. This sudden compression can push pockets of gas over the critical density threshold needed for gravitational collapse to begin, effectively seeding the birth of new stellar nurseries. The brilliant blue knots of star formation we see are often found lining these shock fronts, revealing them as the primary architects of the starburst. They are the cosmic catalysts, the triggers that convert the chaotic energy of a collision into the focused process of creation, forever linking the grand dance of galaxies to the birth of individual stars. One of the most enduring puzzles within the Mice Galaxies centers not on what is present, but on what seems to be conspicuously absent. For astronomers studying this system, a significant mystery has emerged around our 17th strange object, a surprising and unexpected shortage of globular clusters. These dense spherical swarms of up to 1 million ancient stars are considered a standard feature of most large galaxies, including our own Milky Way, which is orbited by about 150 of them. They are the galactic old guard, relics from the universe's earliest epoch of star formation. Based on the masses and types of the two original spiral galaxies involved in this collision, astronomers predicted the merged system should be surrounded by a rich halo containing hundreds, if not thousands, of these ancient stellar cities. Yet, detailed searches have come up far short of those numbers, presenting a cosmic case of missing persons, or rather, missing clusters. Several compelling theories attempt to explain this puzzling absence, and each one reveals a different facet of the violent physics at play in a galactic merger. The first and most dramatic possibility is that the merger itself is responsible for a wave of destruction, literally tearing these ancient clusters apart. While globular clusters are incredibly dense and tightly bound by gravity, they are not indestructible. The gravitational tidal forces unleashed during a galactic collision are of a scale and ferocity that is almost impossible to overstate. As the two galaxies swung past each other, the constantly shifting gravitational field would have subjected any clusters orbiting in the outer halos to extreme and rapidly changing stresses. This could have repeatedly stretched and compressed them, pulling stars away from the outer edges of the clusters each time they passed close to one of the galactic cores or through a dense region of dark matter. Over the millions of years of the interaction, this process of tidal stripping could have effectively dissolved many of the clusters, scattering their stars into the general halo of the new merged galaxy, where they become indistinguishable from the background population of stars. In this scenario, the missing clusters are a testament to the destructive power of the merger, which can erase ancient celestial landmarks billions of years old. A second, less destructive but equally fascinating theory suggests the clusters may not be missing at all, but are instead hiding in plain sight, camouflaged by the very fireworks they help to create. The Mice Galaxies are undergoing a ferocious starburst, flooding their central regions with intense ultraviolet and blue light from millions of newborn stars. This brilliant glare could be creating an observational blind spot. The visible light from ancient red globular clusters would be utterly overwhelmed by the dazzling blue knots of new star formation, making them impossible to pick out with optical telescopes. Furthermore, these same star-forming regions are shrouded in thick clouds of dust, which further absorb and scatter optical light. A cluster that might be perfectly visible on the quiet outskirts of a galaxy could be completely obscured if it were located along our line of sight through the dusty, brilliant central turmoil of the merging galaxies. The clusters could be there, but we simply lack the means to see them through the cosmic smoke and glare. A third hypothesis takes a different approach, suggesting the deficiency might be a problem of birth rather than death or concealment. It's possible the original progenitor galaxies were already unusually poor in globular clusters for their type even before the merger began. While this seems unlikely given our general understanding of galaxy formation, the universe is full of outliers. If they started with fewer clusters, then the merged product would naturally have fewer as well. However, the ongoing collision might also be actively preventing the formation of new globular clusters. The same violent shocks that trigger the formation of superstar clusters might be too disruptive for the more gradual, precise processes needed to create the incredibly dense and stable environment of a true globular cluster. The clusters we do see forming in the mice, like the brilliant superstar clusters, may be destined to dissipate over time, their stars scattering before they can settle into the long-term stability of a globular cluster. This would mean the merger is not only failing to preserve the old, but is also incapable of building new ones to take their place. Resolving this mystery is about more than just taking a celestial census. It strikes at the heart of how we understand the evolution of galaxies and their oldest components. Globular clusters are cosmic time capsules. Their stars are so ancient that they preserve a chemical record of the conditions in the early universe, holding clues about the first generations of star formation. If a major galactic merger systematically destroys them, it could erase a vital chapter of cosmic history. Alternatively, if they can survive such an event, it speaks to their incredible resilience. The search for these missing clusters continues, driving astronomers to use ever more sophisticated tools, from the infrared eyes of the James Webb Space Telescope to peer through the dust, to advanced computer simulations that model the intricate gravitational dance of the merger. Their absence is a silent question written into the structure of the mice, challenging us to determine whether this collision is a preserver of history, a destroyer of worlds, or simply a master of celestial disguise. This incredible X-ray beacon, shining with the power of perhaps millions of suns, presents astronomers with a classic cosmic whodunit. The sheer intensity of its emission immediately rules out common stellar processes. An ordinary X-ray binary, where a star is feeding a stellar mass black hole or neutron star, simply cannot reach these luminous extremes without violating fundamental laws of physics known as the Eddington limit, which describes how much material an object can accrete before the intense radiation pressure blows the incoming fuel source away. So if it's not a typical binary, what could possibly be generating such an enormous output? The investigation naturally branches into two main lines of inquiry, each pointing to an object of profound significance. The first and perhaps most tantalizing suspect is an intermediate mass black hole. This is a class of black hole that has long been theorized but has been incredibly difficult to confirm observationally. We are very familiar with stellar mass black holes, the remnants of massive stars, weighing in at perhaps 5 to 50 times the mass of our Sun. And we know supermassive black holes, the monsters that lurk in galactic centers, weighing millions to billions of solar masses. The space between them, black holes ranging from a few hundred to a few 100,000 solar masses, has been a missing link in the black hole family tree. An intermediate mass black hole accreting material at a high rate could easily explain the incredible luminosity of this source. Its larger event horizon and stronger gravitational pull would allow it to swallow more material and shine brighter before hitting that Eddington limit. Finding one here in the chaotic environment of a galactic merger would be a monumental discovery, providing crucial evidence for how supermassive black holes might grow from smaller seeds by merging with others like it. The second compelling possibility is that we are looking at a common stellar mass black hole or neutron star that is somehow breaking the rules, accreting material at a super-Eddington rate. This would require a very unusual and unstable configuration. One scenario involves a hyper-intense, short-lived feeding frenzy where material is falling in so rapidly and thickly that it becomes geometrically thick and optically thick, meaning the radiation literally cannot escape to push back against the inflow. Imagine trying to see out of a blizzard. The snowflakes are so dense that light is trapped. In this case, the infalling gas itself acts as a shield, allowing the black hole to gorge itself temporarily on a phenomenal amount of material and radiate far beyond its normal limits. Another fascinating idea is that the intense radiation might be beamed directly toward us. If the accretion disk and its associated jets are funneled into a narrow cone, like a cosmic lighthouse beam, and that beam is pointed right at Earth, the source would appear dramatically brighter to our telescopes than it would from any other angle. We would be getting a biased but spectacular view of its power. The reason this particular object is so significant beyond the inherent strangeness of its power is its location. The fact that it is found within the Mice Galaxies is likely not a coincidence. Galactic mergers are known to be triggers for extreme astrophysical phenomena. The same gravitational turmoil that pulls out tidal tails and ignites starbursts can also funnel vast amounts of gas into unusual places and drastically alter the orbits of stars and compact objects. This creates the perfect conditions for either creating intermediate mass black holes through successive mergers of smaller ones, or for forcing binary systems into the precise, high accretion rate configurations needed to become ultraluminous. This source, therefore, is a direct product of the collision itself. By studying it, we are not just studying an oddity. We are using the merger as a natural laboratory to witness the formation and behavior of some of the most extreme and elusive objects in the universe. Whether it is a missing link black hole or a rule-breaking binary, its existence helps us piece together the life cycle of compact objects and understand how the most violent galactic events shape the populations of strange celestial beings that dwell within them. While the colossal structures of gas and stars paint a vivid picture of this collision, there is an invisible architecture woven throughout the Mice Galaxies that guides the very flow of energy and matter. This brings us to our 19th strange object, an unexpectedly coherent and powerful magnetic field that has been revealed through the subtle art of radiopolarimetry. To grasp this, we must first understand that galaxies are not just collections of stars and gas. They are also permeated by vast, invisible magnetic fields. These fields are incredibly weak, trillions of times weaker than a common refrigerator magnet, but because they thread through such enormous volumes of space, they exert a profound influence on how gas collapses to form stars, how cosmic rays travel, and how energy is transported throughout a galaxy. In a calm, isolated spiral like our Milky Way, this magnetic field is generally ordered along the spiral arms like the grooves on a record, following the natural rotation of the galactic disk. The chaos of a merger would seem destined to shred this delicate order, to tangle the magnetic field lines into a hopeless knot of turbulence. Yet, when astronomers used sophisticated radio telescopes to measure the polarization of radio waves coming from the mice, they discovered something astonishing. The magnetic fields within the long tidal tails were not chaotic. Instead, they showed a remarkable degree of large-scale alignment, often running parallel to the immense structures themselves. This was a profound clue. Polarized radio emission is generated by electrons spiraling along magnetic field lines. The direction of the polarization tells us the orientation of those field lines. The discovery of such a well-ordered field, stretching for tens of thousands of light years out in the debris stream, meant that the collision had not destroyed the galactic magnetic field. It had instead stretched and amplified it, imprinting the dynamics of the merger onto the invisible magnetic fabric of the system. This alignment is a direct physical record of the forces that created the tidal tails. As the two galaxies interacted, their original magnetic fields were trapped within the clouds of gas and dust that were being pulled out into space. The same gravitational tidal forces that stretched the stars and gas also stretched the magnetic field lines, pulling them out and aligning them with the direction of the flow. It's a process similar to stretching a bundle of rubber bands. They all naturally align in the direction of the pull. Furthermore, the sheer act of stretching and compressing the gas can actually amplify the magnetic field through a process called dynamo action, making it stronger and more organized than it was before the collision. This tells us that these cosmic events are not just sculptors of visible matter. They are also blacksmiths of magnetic force, capable of forging incredibly large-scale ordered fields in the most unlikely of places, the vast, lonely reaches of intergalactic space. The implications of this magnetic order extend far beyond mere structure. A well-ordered magnetic field can act as a conduit for energy, a barrier for protection, and a guide for future evolution. Cosmic rays, which are high-energy particles accelerated by supernova explosions and black holes, can travel more easily along these field lines, potentially being channeled far out into the intergalactic medium. This magnetic architecture also influences the next generation of stars. Within the tidal tails, the aligned magnetic fields can help support clouds of gas against gravitational collapse, potentially slowing down star formation, or they can guide the flow of gas, funneling it into specific regions to create new stellar nurseries. The presence of this strong, organized field means the tidal tail is not a dead relic. It is a dynamically active structure, with its invisible magnetic skeleton playing a crucial role in determining how it continues to evolve, how it breeds new stars, and how it interacts with the cosmic void. It is a stunning reminder that to truly understand a galaxy, we must learn to see not only the light it emits, but also the invisible forces that shape its destiny. Among the most dramatic possibilities emerging from the study of the Mice's double nucleus is a scenario that sounds like science fiction: the potential ejection of a supermassive black hole from its galactic home. This concept forms our 20th strange object, the runaway supermassive black hole. The idea that an object weighing millions or even billions of times the mass of our Sun could be hurled into the intergalactic void at incredible speeds is almost incomprehensible, yet the physics of a galactic merger makes it a genuine possibility, and astronomers are actively hunting for the evidence within this chaotic system. The mechanism behind this incredible event is a gravitational phenomenon known as the three-body interaction. As the two supermassive black holes in the mice spiral closer together, they form a tight binary system. However, the galactic core is a crowded neighborhood, and a third massive body, another black hole or a dense star cluster, can intrude on their delicate gravitational dance. When this happens, the complex interplay of gravitational forces can act like a cosmic slingshot. To conserve energy and momentum within the three-body system, one of the black holes can be flung outward at a tremendous velocity, ejected from the core and sent on a one-way trip into the darkness. This isn't a gentle nudge. We're talking about recoil velocities that can reach thousands of kilometers per second, more than enough to escape the gravitational pull of the entire merged galaxy. So, what would astronomers actually look for to find such a beast? The search hinges on identifying an incredible disconnect, a brilliant, compact source of energy that is completely decoupled from the visible mass of the galaxy. The most promising signature would be a point-like source of energy, an active galactic nucleus still shining brightly from its accretion disk that is visibly offset from the galaxy's kinematic center and is moving with a detectable and very high proper motion. In simpler terms, they will be looking for a blazing beacon of light that is clearly separated from the main body of the galaxy and is measurably moving away from it. Finding a quasar racing through the emptiness between galaxies would be the holy grail of evidence for this phenomenon. Within the Mice system, the search is focused on the precise locations and motions of the two active nuclei. Are they both perfectly anchored at the gravitational center of their respective galaxies, or is one of them slightly off-kilter? Does the motion of the surrounding stars and gas indicate a single, dominant gravitational source, or are there hints of a second, displaced source of immense gravity? Current observations are incredibly challenging because the two galactic cores are still so close together and enshrouded in dust, making it difficult to measure tiny positional offsets or subtle velocity differences. However, next-generation telescopes like the James Webb Space Telescope with its unparalleled infrared resolution are poised to make these precise measurements, potentially catching a black hole in the very act of being evicted. The long-term fate of such an ejected black hole is a lonely one. It would carry its accretion disk with it, allowing it to shine as a naked quasar for millions of years as it consumes the gas trapped in its grip. But once that fuel is exhausted, it would fade into blackness, becoming a truly dark and invisible wanderer, a supermassive black hole drifting silently through the cosmos, untethered to any galaxy, a permanent monument to the violent event that created it. While definitive proof in the mice remains elusive, the ongoing hunt for this runaway monster pushes our observational capabilities to their limits and reminds us that even the most massive anchors of a galaxy are not immune to being thrown astray by the universe's most powerful forces. Yet for all the brilliant light and furious energy we have explored so far, some of the most telling features within the Mice Galaxies are not sources of radiation, but profound absences of it. Scattered throughout the luminous tails and disks are enigmatic dark patches that stand out in stark silhouette against the glowing backdrop of stars and gas. These are not empty voids, they are our 21st strange object, infrared dark clouds. To the eye of an optical telescope, these regions might simply look like nothing, black splotches where the stars have run out. But when viewed through the infrared eyes of telescopes like Spitzer or James Webb, they reveal their true nature as some of the coldest, densest, and most massive concentrations of gas and dust in the entire collision. The reason these clouds appear so dark is a phenomenon known as extinction. The space between stars is not entirely empty. It is filled with tiny, micron-sized grains of silicate rock and carbon-rich soot, the same basic materials that you might find in a handful of desert sand or the ash from a fire. When light from background stars tries to pass through a particularly dense cloud of this dust, these grains absorb and scatter the light, effectively blocking it from reaching our telescopes. It is the cosmic equivalent of trying to see a car's headlights through a thick, heavy fog. The light is there, but the obscuring material in between makes it impossible to see through. In the infrared part of the spectrum, however, the story changes. While these dust grains are excellent at blocking visible light, they are terrible at blocking longer wavelength infrared light. Furthermore, the clouds themselves, being cold, emit their own faint heat signature in the infrared. This allows infrared telescopes to peer directly into and through these clouds, mapping their intricate structures in stunning detail. What these observations reveal are not simple blobs, but complex, ragged, and filamentary structures. These infrared dark clouds are colossal, often light years across and containing enough mass to form thousands of stars like our Sun. Their existence in the mice is a direct consequence of the merger's chaotic physics. The same powerful shock fronts and tidal forces that compress gas to trigger starbursts in some regions can also, under slightly different conditions, crush vast reservoirs of gas into these incredibly dense, cold, and quiescent pockets. They represent a critical, paused state in the star formation process. Within their frigid interiors, gravity is locked in a silent struggle with internal gas pressure and weak magnetic fields. The material is dense enough that gravitational collapse is inevitable, but the process hasn't yet been fully triggered. They are celestial cocoons in the earliest stages of formation, holding the potential for future stellar birth within their inky depths. This leads to a fascinating and ongoing debate among astronomers. Are we looking at future stellar nurseries or something more exotic? The prevailing theory is that these are indeed the birthplaces for the next generation of stars within the merger. Given enough time and perhaps a nudge from a passing shock wave or the gravitational influence of a nearby star cluster, these clouds will eventually cross the critical threshold and begin to fragment, giving rise to new clusters of stars. However, the extreme environment of the mice opens up another, more speculative possibility. The incredible pressures generated by the galactic collision could be creating conditions unlike anything we see in our own tranquil galactic neighborhood. Some scientists theorize that within the very hearts of these clouds, the density might be so extreme that it could foster the formation of an entirely different and far more massive kind of star. We could be looking at the nurseries for superstar clusters or even the birthplaces of intermediate mass black holes, formed not from dying stars but from the direct collapse of these primordial gas clouds. Their profound darkness is not an end but a beginning, a silent, hidden chapter in the story of this collision, holding within it the potential for either common creation or something truly extraordinary. Moving from the cold, dark nurseries of future stars, we now shift our focus to one of the most energetic and puzzling signals ever detected from this cosmic collision. Astronomers using space-based observatories like the Fermi Gamma-ray Space Telescope have detected faint but significant gamma-ray emissions emanating from the general direction of the Mice Galaxies. This is our 22nd strange object, an unresolved gamma-ray mystery. Gamma rays represent the most energetic form of light in the universe, carrying billions of times more energy per photon than visible light. Their detection immediately signals that tremendously violent and high-energy processes are at work, but pinpointing the exact cause in a complex environment like the mice opens up a thrilling investigative saga with implications that stretch to the very edge of modern physics. The first and most obvious suspects in any astronomical whodunit are known astrophysical objects. In the case of gamma rays, the usual culprits are often high-energy particle accelerators. The merger environment of the mice is teeming with potential sources. The powerful shock fronts from the colliding gas clouds, the fierce stellar winds from massive newborn stars, and the remnants of countless supernova explosions all act like natural particle colliders, accelerating protons and electrons to nearly the speed of light. When these ultra-relativistic particles collide with photons or other atoms, they can produce gamma rays. Furthermore, the system's ultraluminous X-ray source and its potential intermediate mass black hole could also be contributing to this high-energy signal. The complexity lies in the fact that the resolution of gamma-ray telescopes is not sharp enough to pinpoint the exact location within the mice system. The signal is like a blurry smudge on a map, making it incredibly difficult to tie it definitively to any one of these known objects. This uncertainty is what allows for a far more exotic and electrifying possibility, that we are witnessing the indirect signature of dark matter annihilation. This theory is one of the most sought-after goals in all of astrophysics. The leading theoretical models suggest that dark matter could be composed of weakly interacting massive particles, or WIMP. If these hypothetical particles are their own antimatter counterparts, then when two WIMP collide, they could annihilate each other in a flash of energy, producing a shower of standard model particles, including gamma rays, in the process. The dense dark matter halos of galaxies are thought to be the very places where such collisions would be most likely to occur. A galactic merger which stirs and compresses these halos could significantly boost the annihilation rate. The detected gamma ray signal from the mice could therefore be the first faint whisper of dark matter revealing its true particle nature, a direct signal from the universe's most elusive substance. However, the scientific process requires extraordinary evidence for extraordinary claims. The gamma ray signal from the mice, while compelling, is not yet a smoking gun. It could still be explained by a population of unresolved, more mundane sources. For instance, a large number of pulsars, the rapidly spinning, ultra-dense cores of dead stars, could be collectively contributing to the signal. These cosmic lighthouses beam out radiation across the spectrum, including gamma rays, and a starburst environment like the mice would be expected to produce them in vast numbers. Until we can achieve better angular resolution in gamma ray astronomy, or find a correlated signal in another channel like neutrinos, the mystery will persist. This unresolved puzzle perfectly encapsulates the challenge and the excitement of modern astronomy, where a single, faint signal can point toward either a new understanding of known physics or a revolutionary window into an entirely new realm of the cosmos. Beyond the grand tidal tails and brilliant star clusters, there exists a far more subtle and intricate structure woven throughout the Mice Galaxies, a ghostly fingerprint of the gravitational forces at work. If you look very carefully at the deepest, most sensitive images of this system, you can make out faint, wispy tendrils of light arcing through the darkness, connecting the two galaxies in a delicate web. These are stellar streams, and they represent our 23rd strange object. Unlike the massive, coherent tidal tail, these streams are thin, fractured rivers of stars, each one telling a unique story of a specific point in time during this colossal gravitational encounter. The formation of these streams is a beautiful and violent demonstration of gravitational physics. Imagine the countless billions of stars that once peacefully orbited within the disks of the two original spiral galaxies. As the galaxies began their close pass, the gravitational pull from each one didn't just act on the galaxies as a whole, it acted on every single star within them. However, the strength and direction of that pull varied dramatically depending on a star's precise location. Stars on the far side of a galaxy felt a slightly different tug than stars on the near side. This difference, a tidal force, began to subtly alter their orbits. For many stars, this change was catastrophic. Their original, stable orbits were disrupted, and they were flung out into new, chaotic paths that often took them far from the main bodies of the galaxies. Over time, stars that were stripped away at the same moment and with similar velocities began to travel along similar trajectories, forming these long, coherent streams that trace their orbital paths through space. What makes these faint rivers of light so invaluable to astronomers is that they act as a living record of the merger's history and dynamics. The specific path of a stellar stream is exquisitely sensitive to the gravitational landscape it travels through. By meticulously mapping the position, density, and velocity of stars within a stream, scientists can effectively reverse engineer the events that created it. It's a technique known as galactic archaeology. A sharp bend in a stream might indicate the gravitational influence of a previously unknown dark matter subhalo, a smaller clump of dark matter within the larger galactic halo. Variations in the stream's thickness can tell us about the rate at which stars were stripped from their parent galaxy. A sudden surge of material might correspond to the moment of closest approach between the two galaxies. Furthermore, by studying multiple streams, each formed at a different stage of the interaction, astronomers can create a timeline of the entire collision. The oldest, most diffuse streams were likely the first to be torn away during the initial encounter, while sharper, more concentrated streams might have formed more recently as the galaxies swung around for another pass. Each stream is like a single frame in a movie of the collision, and by putting them all together, we can watch the entire event play out in slow motion, hundreds of millions of years after it happened. These faint, almost invisible structures are therefore not merely debris. They are the ultimate cosmic witnesses, their very shapes encoding the secrets of the forces that created them and providing a detailed map of the invisible dark matter that guides their every move. But to truly understand the forces shaping the future of this collision, we must peer deeper into its heart than visible or infrared light can take us. We must descend into the frigid, dark realms where star formation truly begins, within the dense clouds of molecular gas. For our 24th strange object, we turn to the unparalleled vision of the Atacama Large Millimeter Array, or ALMA, a telescope designed to see the universe in the light of these cold gases. What ALMA revealed in the mice was not a simple, chaotic mess, but a breathtaking and unexpected complexity in the distribution and structure of the molecular gas, a hidden architecture of twisted and compressed clouds that tells a far more intricate story of this merger than we could have ever imagined from optical images alone. Molecular gas, primarily in the form of hydrogen molecules, is the raw, cold fuel for star formation. Unlike the atomic hydrogen that makes up the vast bridge between the galaxies, this molecular gas is cold enough and dense enough to collapse under its own gravity and form stars. ALMA's incredible resolution allows it to map the emission from specific molecules like carbon monoxide, which acts as a tracer, revealing the presence and detailed structure of these otherwise invisible fuel reservoirs. The expectation might have been to find these dense clouds concentrated in the brilliant blue starburst knots, but ALMA maps presented a far more nuanced and fascinating picture. The molecular gas is distributed in a wildly complex pattern, with intricate filaments, compressed shells, and surprisingly dense pockets located far from the obvious sites of star formation. This complex distribution is a direct physical record of the violence of the collision. The gravitational tides and powerful shock fronts have acted like a cosmic hammer and anvil on the galaxy's interstellar medium. Vast clouds of gas have been slammed together, creating incredibly dense, compressed regions where the pressure is so high that star formation is all but inevitable. These are the engines powering the brilliant starburst. But in other areas, the same forces have acted like a whirlwind, stretching and shearing the gas into long, thin filaments that spiral through the tails and bridges. These twisted patterns are frozen snapshots of the gravitational forces at the exact moment the gas was pulled out, a fossil record of the merger's dynamics written in cold gas and dust. The collision hasn't just moved this gas, it has sculpted it, folding it into shapes that reveal the direction and intensity of every push and pull. Perhaps the most surprising discovery from ALMA is the presence of significant reservoirs of this cold, star-forming gas far out in the tidal tails, far from the gravitational safety of the galactic cores. This was a profound revelation. It was previously thought that material ejected into the tails was effectively lost, too diffuse and too distant to ever form new stars in meaningful numbers. ALMA showed this is not the case. Dense, massive clouds of molecular gas have survived the violent expulsion and are now riding the tidal tails out into intergalactic space. This changes everything we thought we knew about the long-term impact of galactic mergers. It means these collisions don't just trigger star formation in their cores, they can also seed star formation in the profound emptiness between galaxies, potentially giving rise to isolated communities of stars that live and die in the darkness, completely untethered from any major galaxy. The intricate maps from ALMA are therefore more than just pretty pictures. They are a forecast of the future, showing us where new stars will be born for millions of years to come. and proving that the creative reach of a galactic collision extends far beyond the limits of the galaxies themselves. Now we turn our attention to one of the most dynamic and puzzling aspects of this entire cosmic collision, a feature that makes the heart of one of these galaxies behave less like a steady beacon and more like a flickering candle in a cosmic wind. This is our 25th strange object, the variable active nucleus. While we've established that both galactic cores are active, one of them has been caught in the act of an incredible performance, exhibiting drastic and unpredictable changes in its brightness across the entire electromagnetic spectrum. Unlike the steady, relentless output of a typical active galactic nucleus, this one flares and fades over timescales that can range from months to years, presenting a captivating mystery about what exactly is happening so close to this supermassive black hole. To an astronomer, such variability is a powerful clue. The timescale of the brightness changes can actually tell us about the physical size of the region responsible. Because nothing can travel faster than light, a source cannot flicker significantly faster than the time it takes light to travel across it. If we see the brightness of this nucleus double in a matter of months, it tells us that the engine powering this change, likely the innermost, hottest part of the accretion disk, must be smaller than a few light months across. This is an astonishingly small volume of space to be generating enough power to outshine an entire galaxy, and it underscores the incredible energy densities at work just outside the event horizon of this multi-million solar mass beast. So what could be causing these dramatic shifts in luminosity? Astronomers are investigating several compelling possibilities. The first and most straightforward explanation is a simple change in the black hole's diet, a fluctuation in its accretion rate. Imagine a steady stream of water flowing into a drain versus a sudden surge from a turned-on faucet. The gravitational turmoil of the ongoing merger could be funneling gas toward the black hole in clumps and waves rather than a smooth river. A particularly dense cloud of gas falling in would provide a sudden feast, causing the accretion disk to heat up intensely and shine brighter before settling back down as the meal is consumed. This would create a noticeable flare in brightness across all wavelengths that then gradually fades. A second, more structural theory involves not a change in the food supply, but a shifting veil in front of it. This is the obscuration hypothesis. The core of a merging galaxy is a filthy place, filled with swirling clouds of dust and gas. It's entirely possible that a large, dense cloud of this material could drift directly across our line of sight to the brilliant accretion disk, temporarily blocking its light and making the nucleus appear to dim from our perspective. Later, as the cloud moves on, the brightness would return to normal. This would be like a cloud passing in front of the sun. The sun's output hasn't changed, but our view of it has been temporarily obscured. This scenario would often show a specific signature. The shorter, bluer wavelengths would be blocked more effectively than the longer, redder ones, as smaller light waves are more easily scattered by dust. However, the extreme environment of the Mice Galaxies invites speculation about even more exotic causes. Could the variability be linked to the black hole's spin or to instabilities in the accretion disk itself that are triggered by the gravitational shocks of the merger? Perhaps the flickering is evidence of a second, smaller black hole orbiting the primary one, its gravity periodically disturbing the inner edge of the accretion disk and causing surges of material to fall in. Each of these scenarios would produce a slightly different pattern of variability, a unique fingerprint in the light curve that astronomers can use to diagnose the precise physics at play in this most extreme of environments. Monitoring this variable nucleus is therefore like watching a live diagnostic feed from the edge of a black hole. Every flare and every dimming event is a data point, telling a story about how matter behaves under the most extreme gravitational stresses imaginable. It provides a real-time look at how a galactic merger can directly influence the feeding habits of the most destructive objects in the universe, offering insights that are simply impossible to gain from studying a quiet, stable galaxy. This flickering heart is a testament to the dynamic, chaotic, and utterly fascinating nature of the Mice Galaxies, proving that even the monsters at the center of the chaos are not immune to the cosmic storm raging around them. As we follow the grand, sweeping arcs of the tidal tails out into the profound darkness between the galaxies, our attention is caught by tiny, brilliant points of light that seem to be sailing in complete isolation. These are not foreground stars from our own galaxy, nor are they distant background galaxies. These are our 26th strange objects, intergalactic star clusters, entire communities of stars that have been cast adrift in the ocean of space, far from the safe harbor of any major galaxy. Their very existence is a direct and stunning consequence of the violence of this collision, and they act as celestial buoys, marking the currents of material that were flung outward during the galaxy's gravitational encounter. The formation of these isolated clusters is a fascinating story of creation amid destruction. They did not form in place from nothing. They were born within the galactic disks of the original spirals, only to be violently evicted. During the first close pass of the two galaxies, the immense tidal forces did more than just pull out long streams of gas. They also perturbed the orbits of entire star clusters that were already in existence. Dense, gravitationally bound globular clusters and younger, massive open clusters found their stable orbits suddenly and catastrophically disrupted. For some, the gravitational kick was so strong that it exceeded the escape velocity of their host galaxy. They were flung out into intergalactic space, carrying with them the ancient history of their birthplace as they began an eternal journey through the void. But there is a second, even more remarkable origin story for some of these clusters. They are not exiles, they are newborns formed in the very depths of the tidal tails themselves. As the enormous clouds of gas were pulled out from the galaxies, they were compressed and shocked. Within these isolated rivers of gas, conditions sometimes became perfect for a spontaneous burst of star formation. The gas collapsed under its own gravity, fragmenting to form not just individual stars, but entire new clusters, hundreds of thousands of stars strong, all born together in the darkness between galaxies. This means we are looking at objects that have never known the gentle rotation of a galactic disk. They were born as orphans in the intergalactic wild, their first light shining on no planets, illuminating only the empty space around them. Studying these isolated clusters provides astronomers with a uniquely clean laboratory. Within a typical galaxy, the light from a star cluster is contaminated by the diffuse glow of billions of other stars in the background, making precise measurements difficult. Out here in the emptiness, these clusters stand alone against the blackness of the universe. This allows for exquisitely precise measurements of their mass, their age, and their chemical composition. By analyzing their light, we can determine exactly what they are made of. If a cluster is old and metal poor, it tells us it was likely ripped from the ancient halo of one of the progenitor galaxies. If it is young and metal-rich, it signals a recent birth within the enriched gas of the tidal tail itself. Each cluster becomes a time capsule, preserving a specific moment in the merger's history. Their existence also forces us to reconsider the very concept of a galaxy's territory. We traditionally think of a galaxy as a defined island of stars, gas, and dark matter with a clear edge. The discovery of a significant population of stars and clusters flying freely in the space between the Mice Galaxies blurs that boundary beyond recognition. It shows that a galactic collision does not just rearrange the furniture within the house, it catapults pieces of that furniture far out into the yard and even builds new pieces out there. This ejected population forms a faint but vast stellar halo, a corona of stars and clusters that will forever orbit the merged galaxy, a permanent testament to the violence of its birth. These intergalactic star clusters are the boldest pioneers of this collision, the first to venture into the unknown, showing us that the creative and destructive forces of the cosmos know no bounds. While the grand structures of the mice tell a story of gravitational forces, the true nature of its energetic processes is often revealed not by what we can see, but by what we can dissect. When astronomers train their spectrographs on this system, splitting its light into a rainbow of constituent colors, they uncover a hidden layer of complexity in the form of strange and unexpected emission lines. These are the unique chemical fingerprints of excited atoms, and in the mice they are telling a story of extreme physics. Normally, the spectrum of a galaxy shows familiar lines from common elements like hydrogen, oxygen, and nitrogen. But here, mixed in with the usual suspects, are lines that are far more exotic, signaling conditions so violent and unusual that they defy explanation by everyday astrophysics. The key to understanding these spectral anomalies lies in the concept of ionization. An atom becomes ionized when it loses one or more of its electrons, typically after being slammed by a high-energy photon or a collision with another fast-moving particle. The specific wavelengths of light that these ions emit when their electrons eventually settle back down act as a precise barcode, identifying not only the element present but also its ionization state. In a quiet galaxy, you might see lines from singly or doubly ionized elements. In the frenzied environment of the mice, astronomers are detecting lines that require atoms to be stripped of a dozen or more electrons. This points to the presence of a truly ferocious source of energy, something capable of bombarding matter with photons of incredibly high energy. So what could be powering this intense radiation field? The prime suspects are the same engines we've already encountered, but their collective effect is what creates this exotic spectral signature. The combined fury of millions of massive newborn stars floods the interstellar medium with ultraviolet radiation, efficiently ionizing the surrounding gas. Meanwhile, the shock fronts from supernova remnants and colliding gas clouds act as colossal particle accelerators, smashing atoms apart with incredible force. And at the very heart of it all, the brilliant ultraviolet and X-ray radiation pouring from the active galactic nuclei provides a relentless, searing glare that can ionize gas across vast distances within the galaxy. It's this combination of astrophysical violence that pushes the gas in the mice into ionization states rarely seen elsewhere, creating a spectral tapestry woven with the signatures of highly ionized iron, neon, and oxygen. Some of the most puzzling lines, however, may be pointing to even more unusual phenomena. Certain weak or shifted lines could be the signature of rare elements being forged in the supernova explosions of the most massive stars, elements that are quickly dispersed into the turbulent medium. Others might indicate the presence of powerful magnetic fields influencing how atoms emit light, or even the outflows of material being driven by the intense radiation pressure from the starburst regions. Each unusual line is a clue, a piece of a puzzle that, when solved, helps us build a more complete picture of the extraordinary laboratory that a galactic merger provides, where the laws of physics are tested under conditions we can only dream of recreating on Earth. Yet another layer of this cosmic mystery reveals itself not in visible light, but in the subtle warmth of the dust itself. When astronomers combined observations from infrared telescopes like Spitzer and Herschel, which are sensitive to heat, they constructed a detailed temperature map of the dust spread throughout the Mice Galaxies. The expectation was to find a predictable pattern. The dust closest to the brilliant starbursts and active nuclei should be fiercely heated, while the dust out in the quiet tidal tails should be frigid. But the cosmos, as it so often does, had a surprise in store. The actual map was a chaotic patchwork of hot and cold that defied simple explanation, revealing our 28th strange object, a profound and puzzling dust temperature anomaly. This isn't a minor discrepancy. It's a fundamental challenge to our understanding of how energy moves through a galactic merger. In some regions, vast clouds of dust are far colder than any model predicted, remaining chilled even when bathed in the intense radiation of nearby superstar clusters. In other areas, isolated pockets of dust out in the tidal tails are glowing with an unexpected and mysterious warmth, as if they contain hidden heat sources that we cannot directly see. This bizarre distribution means that the process of heating and cooling the interstellar medium in a collision is far more complex than we imagined. It's not a simple equation of proximity to a major energy source. Other, more subtle factors are at play, turning the galaxies into a cosmic game of thermal regulation that we are only just beginning to understand. So what could be causing this uneven heating? The prime suspect is the incredible complexity of the dust grains themselves. We often think of interstellar dust as a uniform substance, but it's actually a diverse population of different-sized particles and compositions. The larger, micron-sized grains are like tiny rocks. They are inefficient at absorbing energy and take a long time to heat up and cool down. The smaller grains and large molecules known as polycyclic aromatic hydrocarbons, or PAH, are the opposite. They are like microscopic embers, absorbing a single photon of ultraviolet light and almost instantly heating to tremendous temperatures before rapidly cooling off again. The chaotic turbulence of the merger likely segregates these different types of dust, sweeping larger grains into some areas and smaller grains into others, creating a wild variation in how different regions respond to the same energy input. A cloud dominated by large grains might stay cold next to a brilliant cluster, while a cloud filled with tiny grains might briefly flare with heat even when relatively isolated. But the dust's temperature is not just about what it's made of, it's also about what is happening to it physically. The powerful shock fronts racing through the Mice Galaxies play a dual role. In some cases, a shock wave can compress a cloud of dust and gas, dramatically heating it through simple physics. Squeezing a gas increases its temperature. Yet, in a fascinating paradox, that same compressed cloud might then quickly cool itself. The dense gas becomes incredibly efficient at radiating away its thermal energy, especially in specific infrared wavelengths, essentially hitting a cosmic thermostat that prevents it from getting any hotter. This means a region could be experiencing tremendous energy input from a shock wave, but still appear surprisingly cold to our telescopes because it is cooling itself so effectively. The dust temperature map, therefore, is not a simple map of energy input. It is a map of a dynamic and ongoing battle between heating and cooling processes happening across thousands of light years. This anomaly forces us to reconsider the very life cycle of the material within a galaxy. The strangely cold dust reservoirs are of particular interest. Their existence suggests that despite the overwhelming violence of the merger, pockets of the original galactic disks have managed to shield themselves, perhaps deep within dense molecular clouds that are opaque to the heating radiation. These cold pockets are crucial as they represent the future fuel for star formation, preserving the raw materials needed for the next generation of stars long after the current starburst has burned itself out. The unexpectedly warm dust, on the other hand, could be signaling the presence of completely overlooked energy sources, such as a population of faint, aging stars or even the gentle but pervasive energy input from cosmic rays accelerated by forgotten supernova. This thermal puzzle reminds us that to truly understand a galaxy, we must account for every source of energy, from the blazingly obvious to the whisper quiet, and appreciate how the intricate structure of the interstellar medium itself dictates the final temperature of the cosmic dust that fills it. But all this visible matter, from the blazing star clusters to the frigid dust clouds, represents only a small fraction of the true story. To uncover the full mass of the Mice Galaxies, including its most dominant and mysterious component, we must learn to read the subtle distortions in the fabric of spacetime itself. This brings us to our 29th strange object, the profound and almost imperceptible gravitational lensing effects generated by the entire merging system. According to Einstein's theory of general relativity, mass warps the space around it, causing light to follow a curved path as it travels through this distorted geometry. The immense combined mass of the two colliding galaxies acts as a colossal lens, bending the light from thousands of incredibly distant galaxies that lie far behind them in the cosmic depths. To the unaided eye, or even in a standard telescope image, this effect is invisible. It requires meticulous analysis by powerful observatories like the Hubble Space Telescope. Astronomers must carefully study the shapes of countless background galaxies, looking for telltale signs of distortion. Those that lie directly behind the massive foreground of the Mice system are not simply blurred. Their images are subtly stretched and sheared into faint, smeared arcs or into multiple mirrored images of the same object. The degree of this distortion is not arbitrary. It is a direct and precise measure of the total amount of mass in the foreground that is doing the lensing, and crucially, how that mass is distributed. It is the universe providing us with a natural scale to weigh the entire system. This is where the true power of this phenomenon is revealed. By mapping the pattern of these gravitational distortions across the entire field of view of the mice, astronomers can create a detailed mass map, a contour plot showing where the gravity is strongest and where the bulk of the matter actually lies. When this mass map is compared to a map of the visible starlight and glowing gas, the results are startling and profoundly informative. They reveal a significant offset between the peaks of visible matter and the peaks of total mass. The strongest gravitational pull does not come from the brilliant galactic cores or the bright blue star-forming knots, but from regions of seemingly empty space that surround them. This definitive misalignment is some of the strongest indirect evidence we have for the existence of dark matter. It proves that the majority of the mass in the Mice galaxies is not only invisible, but that it behaves differently from normal matter. During the galactic collision, the clouds of gas and dust slammed into each other, creating shock fronts and triggering star formation, slowing down due to friction. The dark matter, which does not interact with light or with itself through any force other than gravity, simply passed through the chaos unscathed. The lensing map shows us the ghostly aftermath of this event. The dark matter halos of the two galaxies, now slightly separated from the visible material they once contained. By studying the precise nature of these gravitational arcs, we are not just weighing the galaxy, we are probing the very properties of the universe's most elusive substance, using the warped light of ancient galaxies as our guide. And so we arrive at the ultimate act of cosmic prediction, our 30th and final strange object, one that doesn't physically exist yet but is born from the silicon brains of our most powerful supercomputers, the future merger simulation. This isn't mere guesswork, it is a profound application of the laws of physics, a digital time machine that allows us to fast forward billions of years to witness the ultimate fate of this celestial dance. Astronomers feed these simulations with everything we've learned about the mice, the current positions, velocities, and masses of the stars, the distribution of dark matter from our lensing maps, the vast reservoirs of gas mapped by Olma. Then they set the clock running, letting the unyielding mathematics of gravity play out the inevitable conclusion of this collision that began 300 million years ago. The first phase of this future is already written in the graceful arcs we see today. Over the next several 100 million years, the two galaxies, locked in their gravitational embrace, will continue to swing past each other. With each pass, they will lose more and more orbital energy, their mutual pull acting as a brake, drawing them closer together. The spectacular tidal tails, those magnificent rivers of stars we see now, will slowly begin to fall back toward the merging core, pulled by the gravity of the combined system. Some of this material will rain down onto the growing central galaxy, while some will be scattered into a vast, diffuse halo of stars, a permanent cloud of witnesses to the violence that created them. The long, elegant mouse-like shapes will dissipate, their distinct forms blurring into a single, chaotic cloud of light. the true climax arrives when the galactic nuclei finally merge. The two supermassive black holes, after billions of years of spiraling inward through dynamical friction and gravitational wave emission, will enter their final, furious orbit. As they whip around each other at a significant fraction of the speed of light, they will radiate away their final orbital energy in a crescendo of gravitational waves, rippling the fabric of spacetime itself. In a flash of unimaginable power, they will plunge together, forming a single, even more massive black hole. The recoil from this merger could be so violent that it might even kick the newly formed black hole out of the galactic center at tremendous speed, creating the ultimate runaway object, though the simulations suggest it will most likely settle back into the core. The final product of this billion-year process will be a giant elliptical galaxy. The beautiful spiral structures of the two original mice will be completely erased, their delicate disks shattered and blended into a featureless, egg-shaped swarm of stars. This new galaxy will be devoid of the cold gas and dust needed to form new stars. It will have been entirely consumed in the final starbursts or blown away by the ferocious winds from the active nuclei and supernova. What remains will be a quiet, red and gold-hued galaxy populated mostly by old, aging stars. The brilliant blue knots of star formation, the turbulent shock fronts, the roaring black holes all will have fallen silent. The system will have entered a peaceful but permanent retirement. Yet, the simulations suggest that even in this final, serene state, strange objects will remain as eternal monuments to the collision. The potential tidal dwarf galaxy forming in the tail may survive as a small, independent and curiously dark matter-free satellite galaxy, forever orbiting its giant parent. The intergalactic star clusters ejected during the chaos will continue their lonely journeys through the void. And the supermassive black hole at the center, now dormant, will hold within its mass the encoded history of its dramatic formation. A story that could only be read by detecting the faint gravitational wave echo of its merger, an echo that will have faded into near silence by the time this future finally comes to pass. This digital prophecy shows us that the end of the collision is not an end at all, but a transformation. A violent, creative, and ultimately beautiful recycling of two galaxies into one. A process that has shaped the universe since its beginning and will continue to do so until its very end. And so, our journey through the chaos and creativity of the Mice Galaxies draws to a close, leaving us not with a simple answer, but with a profound sense of wonder at the sheer diversity of cosmic phenomena a single collision can produce. We have wandered through river-like tidal tales of stellar debris, stood before the blazing fury of twin active nuclei, and witnessed the birth of potential new galaxies from the ashes of the old. We have probed the secrets of dark matter with gravitational lenses, felt the heat of hidden starbursts, and listened for the faint whispers of gamma rays that might signal the annihilation of the universe's most mysterious substance. From the solitary brilliance of intergalactic star clusters to the flickering heart of a variable black hole, each of these 30 strange objects tells a unique chapter in the epic story of this merger, revealing a universe that is far more dynamic, violent, and inventive than we could ever have imagined from our tranquil vantage point here on Earth. What truly unites these disparate wonders is the realization that galactic collisions are the universe's ultimate laboratories. In the calm of an isolated spiral galaxy, physical processes often unfold at a gentle, predictable pace. But here, in the chaotic crunch of two galaxies meeting, the ordinary rules are bent, broken, and rewritten under extreme conditions. Gravity becomes a sculptor on an unimaginable scale. Pressure triggers firestorms of star birth, and invisible magnetic fields are stretched into cosmic guiding wires. These events are not merely destructive, they are intensely creative, forging new objects, triggering new physics, and seeding the future with the raw materials for planets and perhaps life itself. The Mice Galaxies offer us a front-row seat to this creative destruction, a chance to observe in real time the forces that have shaped the evolution of galaxies since the dawn of the cosmos. This grand cosmic dance, happening 300 million light-years away, ultimately holds up a mirror to our own home. The Milky Way and its future collision with the Andromeda Galaxy will one day enact a similar drama, and by studying the mice, we are essentially reading our own distant future. We learn that such mergers are not cosmic anomalies but are fundamental to the life cycle of galaxies. They are the primary mechanism through which galaxies grow, change their shape, and ultimately end the era of star formation, settling into a quiet retirement as elliptical galaxies. Every giant elliptical galaxy we see in the night sky is the fossilized remnant of a violent merger that occurred billions of years ago. The mice show us this process in its vibrant, explosive youth, providing the missing link in our understanding of how the universe built the structures we see today. So the next time you find yourself gazing up at a seemingly static and peaceful night sky, remember the lesson of the mice. Remember that within what appears to be a simple smudge of light through a telescope, there may lie an entire universe of activity, a cosmic drama of creation and destruction unfolding on a scale beyond human comprehension. These aren't just pretty pictures, they are windows into the fundamental processes that govern our universe. They remind us that the cosmos is not a still life but a dynamic, ever-changing, and often violent masterpiece, and that we are privileged to live in a time when we can finally begin to understand its deepest, most magnificent secrets.